So now that we've talked a bit about the concepts of parallel computing, let's talk about how parallel programs are developed in Java. And there's a number of different ways to do this based on different epochs of Java parallel computing infrastructure or frameworks. So we're going to start by talking about the fork-join pool approach. And this is a so-called object-oriented data parallelism framework. They're all important terms. What's a framework? What is data parallelism? What does object-oriented mean? A framework is essentially an integrated set of classes and or objects that collaborate to provide a reusable architecture for a family of related applications. So you'll see when we talk about these things, these are frameworks. They're typified by things like inversion of control and semi-complete applications where you have to fill in the blanks, and domain-specific capabilities, the domain here being the domain of parallel processing. So let's talk about object-oriented parallelism and data parallelism frameworks that are in Java. So the Java fork-join framework defines an object-oriented parallelism approach. There's a great interview by Doug Lee, who is the designer and implementer of a lot of the stuff that's in Java, concurrency and parallelism, where he talks about the motivations behind this particular framework, and it's really worth listening to because he has lots of great insights. It provides a high-performance, fine-grained task execution model, and it's designed to scale up to processors with many cores, as opposed to the earlier concurrent models that were available, such as the Java executor framework, which, as you recall from other discussions, was only really intended to scale up for things like 2 to 4 cores. The fork-join framework can scale up to many more cores, and we'll see how it does that shortly. The focus of this framework is on so-called data parallelism. And the basic idea is that you take a data set, and then you partition it across multiple cores and multiple threads and so on. And then those multiple cores and threads operate on the data in parallel. There's lots of great examples from everyday life. My favorite example that I always use is doing your laundry, where you would have a bunch of washing machines in your dorm or at a laundromat or wherever you do your laundry. And if you were like me when I was in college, you procrastinate doing your laundry, so you end up with like 17 loads of laundry you all have to do at the same time. And you go to the laundromat, and as long as the washers are not all used, you can put your clothes in there and all wash them in parallel, and there's no dependency on one load versus the other. Now, there is a dependency, for example, if you want to dry your clothes, they have to be washed. But once you're done with the washing, you can put them into many dryers and dry in parallel as well. And this particular mechanism that allows this is an abstraction or a class called the Fork-JoinTask. And you'll get a chance to play around with Fork-JoinTask because that's one of the things we do for our programming assignment, is have you work with Fork-JoinTask. A Fork-JoinTask is essentially a lighter weight concurrency or parallelism entity compared to a Java thread. And when I use Java thread here, I should really have been a little bit more precise and say a traditional Java thread, or what we now call platform threads. So a Fork-JoinTask is lighter weight than the Java thread. So if this is the Java thread all pumped up, full of steroids and so on, Fork-JoinTask is like the scrawnier little brother or whatever that is much lighter weight, more nimble perhaps, maybe not as big and bulky, but able to do other things because it's more nimble. In particular, a Fork-JoinTask does not have its own runtime stack, whereas a thread does have its own runtime stack. It doesn't have its own dedicated registers at the hardware and operating system level, kernel level, whereas a thread does. It doesn't have its own thread local storage, whereas a thread does, and so on. So it's basically a thread on a very severe diet. As a consequence of this, a very large number, like millions and millions, of Fork-JoinTasks can run multiplexed over a much, much smaller number of worker threads that are going to reside in a fork-join pool. So the basic idea here is we have a small number of worker threads, which are actual Java threads. The Java platform threads are what they call sometimes carrier threads in the context of virtual threads. There's a small number of those, typically roughly about the same number of cores as there are in the CPU, and we'll talk later about why that is. And then you can have lots of fork-join tasks that run on top of them and are multiplexed. The way that the fork-join framework is designed is it supports parallel programming by solving big problems using divide and conquer. Hopefully you've taken the algorithms course and or the data structures course, either here or elsewhere, and you learned about the concept of divide and conquer algorithms. And basically the idea is you want to split things up into little chunks and then do them in parallel. So here's kind of the way this works. If you have a problem to be solved, then if the problem is small is relative of course, but let's say there's one entity to deal with, then we just solve the problem sequentially. Otherwise, we split the problem up into smaller parts. Usually we divide it in half. And then we go ahead and we fork new subtasks to solve each part. Those can all run in parallel. We then join all the subtasks results incrementally, getting them all kind of pairwise combined together or reduced together. And then finally, we compose a final reduced result from all the sub-results. And the idea here is we can divide things up. And if things go well, then this works great. So let's talk a little bit about the pros and cons of using the fork-join framework. First, we'll talk about the pros. One of the things it does really well, and we're going to cover this in great detail starting probably next class, is talk about work-stealing. And work-stealing is used to maximize multi-core processor utilization. And the basic idea behind work-stealing is that if a thread, a worker thread, a platform thread in the pool of worker threads doesn't have anything to work on, rather than putting itself to sleep or just spinning idly, it looks around at the other threads that are in that pool and looks at their queues. These are actually called decks, double-ended queues. We'll talk more about that later. And it steals work from threads that have more work than they can handle at the moment. So when a thread has nothing to do, it steals work from the end of the deck, and then it goes and processes that. And we'll talk a lot about that. It's very, very cool. And the idea here is to maximize utilization, keep things running at all times, if there's work to do. There's also a special kind of fork-join pool called the common fork-join pool. And we'll talk about that. That's used by default, or it's really used by design, by the Java Parallel Streams framework. And then you can use it by decision with the completable futures framework and other frameworks. And the basic idea there is that you have a common pool of threads that are shared by all the tasks that are running. And that size can be expanded and then contracted using something called a managed blocker. And we'll talk about this when we talk about our programming assignment later, because this is very important for blocking tasks, to make sure that we always have a thread available to do some work if there is work to do. So that's another benefit of using this framework. But as I always like to say, not everything is rainbows and unicorns. There are some downsides with this framework. First and foremost, it can be a bit tedious and error-prone to program. And you'll get some experience doing this because your assignment will cover this. Why is that? Well, it uses so-called Whitebox object-oriented design-based reuse and Whitebox approaches to integration and customization. And that approach is based on inheritance. And so there's this base class or abstract class called Fork-JoinTask. We talked briefly about that. Then there's a bunch of other subclasses, which are actually abstract subclasses that inherit from Fork-JoinTask or extend it. And they define a method called compute, which we'll talk about later. And then you have to go further and extend those classes and fill things in. And it's just a little bit more complicated. One of the other things that makes it somewhat annoying is it was designed for Java 7, which came out in the 2010 timeframe. And at that point, they hadn't added in all the cooler, newer functional programming features that came along in Java 8, which was 2014. So the fork-join framework isn't really well integrated with modern Java's functional programming features. Overcoming these deficiencies motivates Java's parallel functional programming frameworks, in particular parallel streams, which encapsulates the fork-join framework with a nice functional facade. So you can think of these other things we're going to talk about in just a moment as being facades that encapsulate some of the deficiencies with the fork-join framework from a programming point of view, while still leveraging its performance optimizations and its work-stealing and managed blockers and all this other kind of cool stuff. So that's a quick overview of the fork-join framework. We will cover this in a lot more detail here a little bit later.